My name is Niranjan Vaidya. I'm a system architect at Broadcom. And I'll be talking about the third section of this presentation. And the focus is on inline analytics and anomaly detection. So this section now goes a little deeper into some of the methods that we have in our switches to be able to get the data that you've been seeing in some of these use cases before. So it's a little different than before. Let's start with the basics. What is the goal of analytics? We want to identify trends and patterns from the raw data that's being collected, and we want to correlate these observations to actionable metrics. Now, when you look at the raw data, there's a bunch of different types of data that we get. You could get raw counters, drops, queue and buffer usage in your switches, maybe packet samples. You could get route statistics. You could get latency data, and a lot of other things. And you are trying to look at all of this and distill down insights that are actually useful to you. So those desired insights are dependent on your role. Are you a planner interested in capacity? Are you an administrator? Are you a user who's interested in looking at what his applications are doing? Your purpose might be billing, compliance, security, different things, or the time value of the data, the insight that you want might be long-term, or it might be real-time. You want to know it quickly and act on it. Now, in all of these cases, it doesn't matter what your intent is, there's a common goal. You want to be quick about the data, the analytics. You want to be precise, and you want the methods to scale from a single switch to a network, which is running, let's say, 10,000 switches. So let's ask this simple question. What network and traffic characteristics are contributing to observed application performance? We have been talking about application performance in the first two parts of this presentation. So digging a little deeper into the kinds of questions that you might ask, you could start at a packet granularity. What is the packet size mix for a group of applications? How bursty is the traffic? You could think about the problem from the perspective of flows and flow aggregates. So you may want to know how many unique flows are active in a time interval. Or you wanted to dig a little deeper and you want to know what percentage of flows see drops or are being congestion marked. So mind you, this is about flows, not about packets. You could also ask questions from a forwarding perspective if you're an administrator. How well is traffic being balanced across a lag or a ECMP group? You could ask, are too many packets matching deny-ACLs in a time interval? It matters if you have 1 million packets hitting a deny-ACL within a minute versus 1 million packets over a day. If it's within a minute, then that indicates that there is something clearly wrong. You may wonder about the state of the overall infrastructure. How hot is my network running? Are the applications making the best use of available capacity? And especially with large networks, you have multiple paths in there. So the question is about total capacity. Now, when you look at all of these questions and you look at the traditional methods of data collection, what are those methods? So let's dig a little deeper into that. One approach might be that you have a switch and you build a flow table on the switch, or you have counters that are tracking certain things. What is the advantage? You can track every packet that's going through the switch, but then you are typically going to be limited in scale to a few thousand flows because you really don't have the memory to track a very large number of flows. You may take a global approach now. So instead of trying to keep stats on switch, you could do sampling. You could take the data and move it to a centralized collector farm. You could also export your counters out there. And then at the collector farm, you could build a flow table, and then maybe you can infer aggregate statistics on it. And this is really the method that's used today in service provider networks. What is the advantage? Now you do get the scale, you get global visibility, but now you are underestimating for small flows because you're sampling 1 in n. It's a uniform sampling, and you're more likely to miss the smaller mice flows or a single shot flow with one RPC request going back and forth. You can also apply in-band telemetry. And I'm calling in-band telemetry as traditional because we are starting to see it now work in the networks. It's very fine-grained. You can get per flow statistics. But because everything is at a flow level, you are still missing aggregate statistics from the picture. And so the question that we are simply asking here is, can you track more meaningful aggregate statistics on a switch itself? And could you do this precisely, quickly, and at scale? So we'll look at methods for how we can do this, and these supplement the traditional approaches that we have today. And I'll look at this through examples, because that's the easiest way to get the message across. So let's say the first example is we want to track packet sizes and just build a histogram from that. Why is this useful? Because your packet size mix affects network and compute performance. If you have a lot of small packets, then typically they take the same processing load as a larger packet, but you're getting less data across. So you are getting less performance out of your resources if you're seeing a mix of very small packet sizes. What would be the traditional method for getting this insight? You would instrument your servers to capture packet size data, which is not always possible because you may not have control of the servers, or you may have NICs that are doing receive side scaling, and what you're really seeing is an aggregate block of data. You could sample packets to a collector and then have the collector estimate a distribution based on the size it's seeing. But now you're going to get a sampling error, which can be pretty large, and it's going to be biased only in one way. So what would you do on a switch now? What's a good analytics method that you can implement on the switch itself? And the question is, you could program switch logic to generate a histogram of packet sizes. Maybe you can compute min, max, average values. Could you really do it today? Today, no, but that's what we are enabling with the silicon that's out there now. So let's say you had this method working for you. What would it give you? And here's a graph of a sample packet capture. On the y-axis, you see the packet count. On the x-axis, you see different ranges of packet sizes. And they go from 100 to a jumbo size. And we configured 9595, a friendly number to remember. And we're looking at different ranges. So you see a bimodal distribution in this example, where there are a bunch of smaller packets, and then there's something at a higher size in there. Now, you are able to build this information precisely with visibility into every packet that is going through the switch. So we are doing this by observing every packet. There is no sampling going on. We can take the technique and apply it to different criteria. So we can track multiple histograms simultaneously. So it's not just packet size mix. You could now say, I want to do the packet size mix for flows that are matching some kind of a complex ACL rule. You could do a packet size mix for drops that are being observed in the switch queue. You could find out the packet size mix for congestion events. So if flows are going through your switch and you know which packets are getting congestion marked, you can build a histogram of those sizes, and maybe that insight is useful to you because your packet sizes might be the ones that are actually creating congestion. And these insights were not available previously because you had aggregate data at a collector. You did not have the ability to get to this level of detail. Now, this is what the inline tracking enables you with this. And this is not just for packet sizes. It's a histogram. It's a general ability that you could implement out here. Let's look at a second example from a different perspective. And you want to track packet events at scale. Now, what do we mean by packet events? So consider things like a packet drop is an event. A packet matching an ACL is an event. You try to do a lookup of a table. It could be a forwarding fib, it could be a VLAN table, it could be a tunnel or a VPN table, and you had a miss. And you could have a forwarding decision and you could use a specific route, or you could end up not hitting a specific route and only using a default route. Or even an arrival rate is an event for a packet. Now, when this happens, singular occurrences are often less interesting, because it happened once, I forwarded a packet using a default route. Okay, that's not a big deal. But if it happens too many times, and especially if it happens too many times in a time window, then that might be an alert that needs to be looked at. So what are the traditional methods of figuring this out? you could have switch counters that maybe track these events. That's not always possible. And then you read the counters at a high rate. And you escalate if a threshold is crossed. What are the downsides? It's limited by the rate at which counters can be processed in software. You have a CPU with some limits on it. And then it also creates a constant background processing load on your switch CPU. Could you do better? So the inline analytics method is that you simply delegate this to the switch logic. Let the switch logic inform the CPU when the threshold is crossed. And we'll look at a specific example here. So you have a switch, a packet arrives, there is some event tracking logic on the switch, and that's updating a counter. Now, typically, the CPU has to poll this counter fast enough to know when it exceeded a threshold. What you would do with the inline method is that the logic also implements a threshold check. And it automatically generates a CPU interrupt when that threshold is crossed. And you can do this with the notion of a time window. So you can have thresholds be reset at the end of a time window. What would this look like now? So here's a capture. On the x-axis, we have intervals, and 10, 20, 30 are different intervals. On the y-axis, the first graph on the top has packet counts, and the second graph has byte counts. And then there's a red line going through each of them, which is the threshold that was configured. So let's look at the top graph here. You have packets coming in. You are counting the total number of packets for whatever the event is. And in the first interval, you did not exceed a threshold. So it was reset at the end of that. Now, in the second case, you did cross the threshold. So what the logic now does is it generates an interrupt, resets the counter, so that you can start tracking it again within the same interval, because it might happen again. Same thing happens with the byte thresholds. And in this case, the threshold is set low enough that in every interval, you are getting an interrupt saying that this has been exceeded. Now, this mechanism, what it enables you is that you are getting fine-grained data. There is no processing load on the CPU. You are only dealing with these interrupts. And so you can simultaneously track multiple event types, each with independent thresholds. And now your CPU load is decoupled from the event timescales, which could vary anywhere from microseconds to seconds or larger. And you now have a more responsive and scalable design here. So another way, the ability to do something on switch gives you performance characteristics that are not possible before. We'll take a look at a third example. And I know some of you may have questions. We can have questions at the end of this, because all of these are kind of related, and we'll tie them together at the end of the presentation. So let's say now you want to count the number of unique flows in a time interval. Mind you, it's flows, not packets. Why is flow count useful? And there are multiple applications for that. It helps you to better understand your network performance, what kind of resource consumption you have, because especially on your servers, it's the number of flows that end up creating number of sockets and connections. And so there is an impact on the resource usage. It also tells you something about application behavior. Is the application creating a lot of flows? And especially as we go to microservices architectures now, you do see that the flow count goes up. You can identify when chatty sources become active, and that can be used as a DDoS indicator. And we'll actually delve deeper into that later. And it becomes, if you look at the literature, it's a basis for many resource allocation problems. So it's useful. What would be the traditional method of doing this? You would sample the packet and build a flow tracker at a collector. The sampling will result in an underestimate. You catch the big flows but miss the smaller ones. And then the results are delayed because you're waiting at a collector to get enough samples. And it's not easily actionable at a switch level because the inference is happening somewhere else, not on the switch. What's the inline analytics method? We can implement an estimation algorithm on the switch that tracks every packet of every flow. What does that look like? So here's a graph that has on the x-axis the number of unique flows. On the y-axis, we are tracking percentage error versus the known number of flows. Because this is a controlled environment, we know exactly how many flows are being generated in this test setup. And then we have 3 different runs, series 2, 3, and 4, which give you the value. Now, what this flow count estimation in the switch data path is doing is using a very small number of tracking counters. It's giving you the actual number. And the error here, once you hit a smaller critical threshold of flows, is within plus or minus 5%. So we are able to track on switch with a very controlled error bound what the number of flows are that have been going through a switch in a given time interval. Again, key points, we are observing every packet. There is no sampling, which means that you are not going to miss the small flows or even single shot RPCs. The algorithms can estimate to millions of flows with controlled error bounds. We can simultaneously track multiple estimates. You can have an estimate of the number of flows that match a rule, which could be identifying applications, which could be identifying customers. The number of flows forwarded using a default route. So you can tie this to your forwarding data structures in your pipeline and get insight into how many packets actually used your route table and how many packets did not. You can get an idea of flow distribution across an ECMP group. So you get a sense of how fair you are when you disperse traffic across multiple paths. And the method here relies on programmable infrastructure. It's not hard-coded. So you have a flexible definition of a flow spec. It could be a 5-tuple or other, and we will get into an example where it's other in there. But here's things that we could now do that we could not do before, right? So this is a third different method here that we are talking about. Now, this section was about inline analytics and anomaly detection. So what is the goal of anomaly detection? It is to identify outliers in the observed data and patterns. So we looked at 3 different methods, but now you have a higher level goal, which is figuring out outliers in observed data. Can inline methods help? Can we change the nature of the problem by doing more processing on switch so that anomaly detection, which today is really an inference task at a distributed level, could that be done in a better way with insights from the switch? And we'll take a case study. We'll look at inline DDoS attack detection. The best way to explain this is through an example that people will understand. So what is inline DDoS attack detection? The problem is that you have many attack vectors which are affecting the resources in your usage, in your network. And you want to identify these attack vectors, which may be varied. So there is no single attack that really happens, but there are different things that can happen. And you want to help identify them and then react to them later. So what is the traditional method here? Typically switches provide minimal insight in this case. And the reliance is on special middle boxes. So you could have firewalls, proxy servers, IDS devices, and you funnel your traffic through them, and they have special intelligence to figure out what's going on. Or you can instrument your servers and then process syslogs. That's typically the method today. Could you do better? Now, you have to admit upfront that DDoS detection is a vast space. There are multiple attack vectors, they keep changing. There isn't a single way to detect them or a single way that someone will attack them. So you really, you would be presumptuous to say that you can do everything on a switch, but you can give better intel to the global watchdogs that you have. And if you are doing this at every switch in your network, you are enabling horizontal scaling of the analytics. So that's what we are going after here. And we'll take a look at 2 examples, detecting port scans and detecting TCP SYN floods. So what is a port scan? it's basically clients trying to see which ports are open on different servers. And you want to identify when clients are doing this. Now, the challenge here is that port scans may be distributed across bot farms. They may be spread out over a long interval. So it's not like someone is probing a server at a very fast rate using Nmap or something like that, but it's slow, distributed over a period of time. And the queries might be coming from different clients, not from the same client. So one of the methods you can use here is relying on flow count estimation. Now, in this case, you would define your flow spec as the destination IP plus the L4 protocol plus the destination port. And then now you count the flows for this flow spec. In a protected network, you have a fixed number of servers with well-known services running on them. So there is an upper bound to what would be the valid ports in use. So the count that you have will peak, and then it will plateau over time. But if the count keeps increasing, then it indicates that someone is probing different permutations of DIP and L4 addresses to figure out what is open. So you now have insight into what might be happening. And this is coming from all of the switches in your network, not from a single point. So you are able to now jumpstart the whole process of figuring out, is it really an attack? And what should I do about it? A second example is detecting TCP SYN floods. Now, what's a normal TCP connection sequence? It's a three-way handshake to open a connection. So a client sends a SYN, the server responds back with a SYN ACK, and now the client sends another ACK saying, yes, I'm ready to start the connection. And then you have data transfers and data ACKs from both sides. Now, what's an abnormal traffic pattern here? You have one or more clients sending TCP SYNs to one or more destinations, but not responding to SYN ACKs with a client ACK. So the picture on the right now shows you have a SYN that was received at a server. It responded with a SYN ACK, but then nothing happened, and the server is holding on to that connection state, the partial connection state, and it's retransmitting the SYN ACKs for a while before it decides to drop the connection. Now, if too many of these happen over a period of time, you're going to end up using resources on the server. There are methods for taking care of this, SYN cookies, for example. But you could do a little better if your switches had the ability to track this. So what are the different ways you could do it? And we'll look at three different methods here. The first is using event alerts. You could track the total number of SYNs and the FINs that you see going through the switch, and then figure out what the imbalance is. And you can do this on the switch itself, computing the imbalance. So if you see that imbalance going high, you can generate an alert, especially if it crosses a threshold. And that becomes an indication that something is wrong because you're not seeing the parity that you should see. In a flawless network with everyone running legally, the ratio would be 1. But you're going to see this go high if that's not the case. Another method would be to rely on flow count estimation. And you can track the active flow count. You can filter on the TCP SYN packets that you're seeing. You can track the estimate across multiple time intervals. And if that count is monotonically increasing and crosses a threshold, then you can generate an alert, because now you are clearly seeing something abnormal going on. And you can now add in smarts later on to keep track of estimates at different intervals of the day, different times of day, because your activity is going to change depending on the time of day. And have alerts that are specific to what you think is normal for that time of day. Now, these two methods, they track aggregate statistics. There is no indication of which servers are under attack at this point, right? So can you help with that? And yes, you can. So the first is that you can supplement by tracking per connection TCP protocol state inline, right? So you can see what is happening on a connection basis for IP addresses that are important to you. And this is typically the server addresses. And you can iteratively update the tracking rules to narrow which subnets are being targeted. And we have a demo that goes into that. Now, let's look at the first part here. Is how do you supplement by tracking per connection state? The top part shows the flowchart that you have logic that is tracking client handshakes. So you're looking at SYN acts, fins, and resets. And the key part here is that you do not want to track both the client and the server traffic, because in these networks today, unless the switch is a gateway device, it's very likely that the two traffic directions might not be going through the same switch. They might take different paths. So you cannot assume in your algorithm that you have visibility into both sides of the traffic. You have to assume that you're looking at either the client or the server. And we're looking at the client here. Now, if you look at the table below, it's a partial state machine that's being shown, that we are tracking the counts for SYN as well as ACKs. We have an imbalance counter that is being updated. And now, if this counter goes beyond a threshold, you can have policy. So you can now capture the packet for further analysis. You can decide that I'm going to map this traffic to a low priority queue, so that because it's suspect now, or you could start dropping in there. And you can identify who are the victims by this method. Let's now get into a demo, and we have our friends at University of Oregon who put this together based on what we have, plus based on technologies that they are developing. So you see a combination of how something can be built on top of what's available in the silicon.
Hi, this is Chris Misa from the University of Oregon. I'm a PhD student who has been working on developing a runtime programmable telemetry system based on Broadcom's flow tracking capabilities. I'll be giving a brief demo of the system's capabilities around a single high-level example telemetry task. So the task that we'll look at in this demo is essentially detecting SYN flood attacks. So this is the scenario where we have a large number of web servers behind a border switch, and we can monitor traffic on that switch in order to detect this attack. We further break the attack detection task into two steps. So in the first step, we want to determine if a SYN flood is occurring, and we base this on the ratio between SYN and FIN packets over all traffic. And in the second step, we want to locate the SYN flood victim so that we can deploy some sort of mitigation efforts. And this step is realized in the telemetry system by iteratively zooming in on destinations that are receiving large numbers of SYN packets. To give a high-level quick overview, our system is essentially a software stack that functions as a control plane over Broadcom switches telemetry capabilities. So we have a graphic user interface that operators can use to describe telemetry tasks, and this interface uses a high-level language we've developed to specify flow tracker rules. Tasks are then evaluated by a runtime server that automatically decides which queries to execute, and it sends these queries to a switch module that we've developed to expose the switch's telemetry capabilities as a service. So the switch module takes care of handling low-level details of communication with the agent running on the switch that speaks in SDK, and also collecting results and parsing those back into a form that's easy to interpret for the runtime and the graphic user interface. We'll go into the demo now. So our graphic user interface runs in a web browser. Looks something like this. As you can see, we have a number of nodes, and they're connected by these heavy black wires which transfer control between nodes, and the colored wires are transferring data between nodes. So on the left we have this SYN-FIN module, which is computing this SYN-FIN packet ratio, and it's emitting that as a data wire to a graph, and also to a node that's comparing that with a threshold, so that once that ratio goes above a threshold that we've defined as 3 here, then we move into this other node, which is actually finding the SYN victim. So I have two simple sort of traffic scenarios to drive this demo. The first is meant to sort of represent normal traffic, and so it has an equal number of SYN and FIN packets, just one of each. The second type of traffic I have is representing attack traffic, and so here we have a larger number of SYN packets with no FIN packets. So I'll start by sending the normal traffic. And then we'll move over into the graphic user interface and start up this flowchart. And while the flowchart runs, we have a number of feedback that's provided to the user. So we show in green which node is being executed as determined by these control flow wires. So we're essentially looping around executing the same node multiple times. But we're also able to show the results that are computed and returned from the Broadcom switch. So we see that we've computed the sin-fin ratio is about 1 year, which is exactly what we would expect. And we can produce graphs of this over time. So let's see now what happens when I send both normal and attack traffic. So this is the scenario that the attack has been initiated against one of our servers. So we notice already, we can see that this sin-fin ratio is spiking, and it's quickly exceeded our threshold that we set as 3, and our runtime system has then switched over to emit the queries that are generated by this find sin victim. So we can go in and we can watch this process actually happening. You can see which queries it's executing in our telemetry query language in order to zoom in and find the victim. So it's iteratively increasing the mask length here, and eventually it'll find I'm attacking 10.10.20.20, I believe. So eventually, once this iterative search process is completed, then this node will pass control to just a regular sort of print statement here, and we'll be able to see here, there it comes, that we've detected this sin-flood victim 10.10.20.20. This concludes my demo. Thank you for watching.
Okay, so thank you, Chris. To summarize this, inline on-switch analytics are key to observing fine-grained network and application behavior. They allow you to generate accurate statistics at scale, and we can detect outliers and react in real time. Okay. Now, in the interest of time, what I will do is I will go to the final takeaway of this presentation, and we can have Q&A after that. So we started by looking at this picture where on the bottom row, we describe different methods of how you can get information from switches in a sophisticated manner. We looked at the top row, which was the intent, the visibility to the user who is using these methods. So you could use it for root cause analysis, SLA monitoring, or anomaly detection. And there is now a collective framework that sits on top of this. The collective framework that we have is based on BroadView. You can customize the granularity at which information is exported. You can only export the data that you want. The alerts can be real-time. It can include security events. And then the format for which this is exported is a standard IPFix format, and anyone who understands that format can receive this information. We have our own AIOps analytics and collector system on top, but you can also have a third-party collector or an in-house collector in here. So this is really building up a complete solution from silicon to the frameworks that are sitting in the silicon or on top of the silicon to a network-wide view of what is happening in your network. Now, final closing thoughts. BroadView Plus enables a comprehensive telemetry solution. We can do proactive, fine-grained monitoring with actionable alerts at scale. It is closely integrated with advanced silicon capabilities. And that includes both the capture of data as well as the ability to export it from the switches. And then there is an extensive ecosystem built around this solution that allows different niche markets to be addressed by it. And we'll leave you with the final thought that this is the pitch line, which is BroadView Plus improving the application experience with best-in-class TCO.